So, good morning, everybody. What I'm going to show in this demonstration is the actual application of the Sub-Nyquist ultrasound, Sub-Nyquist sampling to wireless. If we look at the standard high-end ultrasound system, we can see it is very large, and our motivation is since the state-of-the-art high-resolution ultrasound systems are large and expensive, and due to the high sampling rate dictated by the time domain beamforming, all the processing is being done locally. In the future, in next generation systems, what we'd like to see is only the ultrasonic probe being the front end used by the doctor who is performing the test, and all processing can be done in the cloud only if we manage to reduce the amount of data that has to be transmitted from the probe to the processing system. So, data rate reduction is the enabler for wireless probes and remote processing. What you see here is the configuration of the system, actually, obviously not to scale. Yes, this is a wireless probe, like Robert is holding. Can you show us, please, the wireless probe? This is a probe which we are going to make wireless. This is a server that is located somewhere in the world, somewhere in the hospital cloud or whatever. And this is a handheld device which will display the image. And the enabling technology is only if we manage to transmit raw data at a very low rate over a wireless network, then it can be enabled. So the wireless probe transmits the data over a wireless link to a server. Beamforming and image reconstruction are performed by the server, and the image is sent for display on a monitor or a tablet. Now, this monitor or tablet can be held by the doctor, but also can be monitored by other consultants while performing the test. So this is another advantage of the wireless system. Now, I saw in the registration that there are people from Intel who joined this day, and I'd like to thank you for the IPP library that has enabled very fast processing on the server, and also the VLSI laboratory that have enabled demonstration of the feasibility in a silicon chip, which we are going to see next. So the approach, as I said, is a client-server implementation. The client, which is in the probe, only performs the Sub-Nyquist frequency domain sampling, and the data transmitted to the server where beamforming and image reconstruction are performed. Now, we have the design of the hardware for front end in order to demonstrate that it is feasible, that it's not only theory, but we can make it a real instrument that is used by doctors. So what you see is what we have in the ASIC that we ask the VLSI, the assistants of the VLSI laboratory to design. So this chip will be inside the probe, the ultrasonic probe, and it is doing demodulation, decimation, and pass the samples to frequency domain, and then a subset of this frequency domain samples are transmitted over a channel. Now, if we compare versus the state-of-the-art systems that sample at 50 megasamples per second, in these systems you get 23 gigabits per second to get the imaging in real time, while without sampler chip it is merely 517 megabits per second, which is a saving of 44 times. And these 517 megabits per second can be transmitted over a standard home router, which in 802.11g provides 600 megabits per second. So, and then this is what we got from the VLSI laboratory that after a few months of work have provided the layout and post-layout simulations that prove that this chip is feasible. Now, the demo that we are going to see now is as follows. We have the client. The client emulates the chip because the chip was not produced yet. So this box is emulating the chip. Robert will be using the probe to image a phantom emulates the human tissue, and we transmit it over a Wi-Fi link to a server, and the server is right here, this server. This is the server, and this is a screen of the server, which will demonstrate what we see. Now, in order for all of us to see the image, I will, and please turn off the light. Yes, thank you. And now, Robert, completely, turn off the light completely. Yeah, off the light, thank you. Now, Robert is imaging the phantom, and move it a little bit so you can see the output rate. So I think it's the first time, at least as far as I know, that sampling is used over wireless ultrasound to demonstrate the feasibility of wireless ultrasound. And now, Robert, turn off the, keep the light off yet. Robert, can you show us how it is on the tablet? You can see it's a tablet, so it's small, but you can see the moving imagery which we have done on the tablet, the same of the same demonstration. Can you turn the light on, please? Our next demonstration is an in vivo. We have started to collaborate with the Sheba Medical Hospital. And I'd like to invite Dr. Shai Taiman Yarden, who is a senior cardiologist and electrophysiologist that will describe what we are seeing in the in vivo movie. Shai, this is a microphone for you.
I have a strong voice, but hello everybody. Thank you very much for being here. So actually, this is the first time we tried it on a person who is right here, and what we can see here is actually the heart itself. You can see it beating as we talk. What we see here is called the parasternal short axis, in which we see the aortic valve right in the middle. And over there, all around it, are the cardiac structures. This is the right ventricular outflow tract. This is the left atrium. And the right ventricle comes out into the pulmonary artery, which I imaged right here into both pulmonary arteries. So actually, using this exact system, I could do this. I could sample a real person and show all the cardiac structures. And this is what we do actually in everyday use.
Thank you very much, Shai. And when we first met and you started using the system, so it was in the standard mode. It was the commercial system that you use. How do you compare the quality of the image that we got with the commercial system versus what we get by Sub-Nyquist ultrasound?
So it's exactly the same. So actually, what you have today can be used in a commercial system in everyday use in every hospital.
Thank you very much, Shai, for joining us. So now we have a front-end chip that is doing low-rate sampling for wireless applications. So let's see what else can be done with it. And then we've given it a thought, and we said, okay, let's look into the ECG. By the way, Shai is not ready for that, but this morning there was a note in the paper about a monitor that Shai has implanted in a 1.5-year-old girl, and it was some breakthrough, I guess, otherwise it wouldn't appear in the paper. So congratulations, Shai. So the project that Shai is also involved with us is dealing with Sub-Nyquist sampling of ECG sampling and reconstruction at Sub-Nyquist rates. So what is ECG? I guess all of us are familiar with. It is electrocardiography, recording the electrical activity of the heart using electrodes placed on the patient's body. Now, ECG conveys information about damages to the heart muscle and conduction system. Now, what we want to do is to do wireless body sensor net to place a wireless body sensor network which is the next generation of patient-centric cardiology. For example, we don't want the patient to be on the bed all day, only to be monitored. So this is a trend in ECG monitoring. And energy efficiency of wide area sensor networks can be improved through through embedded ECG sampling at Sub-Nyquist rates. So we'd like to see if we can take the same approach to ECG. The compressed sensing of ECG is just other compressed sensing mechanism. We have the ECG signal, low rate sampling, transmit it over a wireless media, and then solve an optimization problem in order to reconstruct the ECG signal. And the optimization problem is the optimization problem which we all know from compressed sensing. Now the performance, the initial performance results which we have, we took an ECG signal and used only 30% of its samples. This is the original ECG signal, and this is the recovered ECG signal. You can see a nice feature here that even the small noise, the sampling noise we had, does not appear here because we use a signal model in order to reconstruct the signal, so it actually performs also a noise reduction. Now, the lab setup, as you will see, is very similar to what you see in ultrasound. This is an arrhythmia simulator, which simulates different waveforms of ECG. This is a sampling device and a laptop which emulates the chip operation, just as you saw here in the demo. And this is just the same server in the hospital cloud that reconstructs the ECG signal. And this is a chip that is to be designed during this project, and I hope that it will come out soon. Thank you very much.